Hey there, students. Welcome to Psych 653 Lab Module 4, where we'll be discussing categorical predictors and regression and nonlinear regression. So if you couldn't tell, this is another component to this module that I'm going to say. We're going to split it up into two parts, where I'm going to encourage you to listen to the first part of the lecture and then do the part one of the assignment. Then go ahead and continue the video once you finish part one of the assignment, and then listen to part two of the video and then do part two of the assignment. So for part one, what we're going to start off by doing is talking about categorical predictors and regression models, and then part two, we're going to talk about nonlinear regression with continuous variables. So let's talk about part one, which is categorical variables and regression models. So for this demo today, we're going to be practicing three different ways of examining categorical predictors in a regression framework. We're going to do dummy coding, effect coding, and contrast coding. So I'm going to go ahead and we're going to dive right into R, and I'm going to have lessons throughout the module to explain what each of these different coding styles is. So let's go ahead and create a new R project. So open up R Studio, create a new R project, go to new directory, new project. We're going to name this module 04. Go ahead and create that project. There we go. And we'll go ahead and download the data set. So go to File, go to your Canvas, go to Module 04 Lab. We're going to download the sleepdata.csv. Go ahead and open this up. Do File, Save As, Browse. And we're going to go to our desktop, Psych 653, Module 04. Save that sleep data. There we go. I'm going to go ahead and exit out. And then we're going to go ahead and create a new R notebook. Go ahead and delete this unnecessary text. And we'll go ahead and name this Categorical Predictors in Regression. And let's go ahead and create this new table of contents as well. TOC:yes. Go ahead and save it. I'm going to go ahead and name this Module for Notebook. I'm going to name it CatPred, for categorical predictors, because we're going to be creating two notebooks throughout the course of this module today. Okay, so we went ahead and did that. Let's go ahead and go to our slideshow and see what we have to do next. So we're going to go ahead and load up three new libraries. I'm going to go ahead and open up my notes, by the way, here. There we go. We're going to use the tidyverse, OLSRR, and the psych packages today, and we will not be using any new packages. So let's go ahead and load those up. Okay, so hashtag load libraries. Insert a new R chunk. Do library, tidyverse, library, OLSRR, and library, psych. Go ahead and run all that. Let it load. There we go. And I'm going to go ahead and run this again, just get rid of all that output. There we go. And the next thing we're going to do, we're going to use the sleep data set. So we've used the sleep data set in the past before. Remember, the main variables that we're going to focus on today are the condition, which remember there's conditions 1, 2, and 3. Condition 1 is the control condition. Condition 2 is the sleep intervention condition. And then the condition 3 is the slip intervention plus a partner condition. And then our outcome variable is going to be sleep hygiene for this. So let's go ahead and we're going to do hashtag import data, insert R, name it this SLP dataset, use an assignment operator, read underscore CSV, and in quotation sleep data.csv. There we go. Then we're going to go ahead and reduce the data set. Go ahead and do this. Do hashtag reduce the data set to just variables of interest. I believe that's the next slide here. Yes. So we're going to do insert a new R chunk. We're going to rewrite over the sleep data set. We're going to do select and then use the sleep data set. And we're just going to have two variables. We're going to have the con variable and the hygiene variable. So go ahead and run this. We should go from 10 to 2 variables. Yep. So within this data set, we have condition and hygiene. We have condition 1 and its appearance and how it works on hygiene, 2 and 3. So you'll notice before up to this point, we've always been working with either binary variables or continuous variables within the regression framework. Today, we're working with a 3-level categorical variable, and regression is going to assume that this is a continuous variable. So we need to tell the regression framework that it's actually a dummy coded variable or a categorical variable, in which case we'll be dummy coding, effect coding, and contrast coding it to tell it that it's a categorical variable. So the next thing that we're going to do is we're going to go ahead and describe the data set. So let's go ahead and do hashtag describe data, insert R. So we're going to do describe and then SLP. Go ahead and run that. Okay, so we have our condition score, which goes from 1 to 3 because there's just 3 groups. We're not really too interested in that one. What we are interested, though, is the hygiene group. This 5.99, this mean score, is going to come up again when we do effect coding and contrast coding as well. Additionally, this isn't in your PowerPoint, but I think I want to do this too. I'm going to do describe data by condition and hygiene. And what I mean by that is we're going to use the aggregate function to get the mean scores of hygiene by condition. Aggregate, so it's going to be, remember, aggregate, it's going to be SLP by our continuous variable, which is hygiene, by equals list there, and then we do SLP by our categorical variable, which is con, and then do comma, MEAN, mean. So we're going to separate this out by mean. There we go. So the mean value for condition 1 is 4.66. I want you to remember that. That's going to come into play a little bit later, and I'll be sure and recall back to it when it comes up. But additionally, condition 2 is 6.28, and condition 3 is 7.03. So these numbers are going to come into play later, and so is this grand mean is going to come into play later as well. Okay? So let's see what we got next. So for parts 1 through 3, we have this kind of generalized research question, which we're going to ask, to what extent do treatment conditions predict sleep hygiene? So we're going to show how different ways to approach this question using different coding methods for categorical predictive variables. We're doing dummy coding, effect coding, and contrast coding. These methods are all somewhat similar, but the coding and interpretations are slightly different. So let's start off with dummy coding, okay? So what is dummy coding and why do we use it? So dummy coding is one of the most common and simplest approaches to evaluating categorical predictors in psychology. I use it quite often. I think a lot of other people use it quite often. It's probably more common than the other 2 coding techniques. I would say if you're going to leave this class knowing one coding feature for categorical variables, I would say dummy coding is probably the most important one. It's the one that you're going to see most often and probably utilize the most often. But we also not say the effect coding and contrast coding aren't important. It's just that dummy coding is probably the most common. But really what's going on is dummy coding allows you to compare the mean difference between 2 levels of a categorical variable, the level that is coded 1 versus the level that is coded as 0. You can specify any variable as a reference group, which is your variable coded as 0. And then you create a new dummy coded binary variable for every comparison you want to make between groups. So essentially what I'm saying here is that if you have 3 groups, you're going to have 2 dummy coded variables. If you have 4 groups, you're going to have 3 dummy coded variables. If you have 5 groups, you're going to have 4 dummy coded variables. And on the next slide, I think I give a pretty good, a better explanation of what's going on. But for dummy coding variables, we'll be converting categorical variables into a series of binary variables. So what that means by that is they're going to be 1s or 0s, nothing else. They can't fit any other criteria at all. So take, for example, these levels of race. We have a level of race/ethnicity, which is 1 is Hispanic, 2 is Asian, 3 is African American, and 4 is white. And within this, we have these 4 variables. We want to have a reference category to white. So we're going to compare each of our different races to white. So what we're going to do is create 3 different variables. It's the number of groups minus 1, so it's 3, to compare to white categories. So what we'll do is for new variable 1, every time it takes on a level of Hispanic, we indicate it as 1, else it's going to be a 0. For our new variable level 2, anytime it takes on a level of Asian, it's going to be coded as a 1. Else it's going to be a 0. And then for our third variable, anytime it takes on the level of African American, it's going to be a 1, else we're going to code it as a 0. And every time white is going to be coded as 0. It will never take on a value of 1. And what we'll be doing here is we're going to be comparing Hispanic to a white race. We're going to be comparing Asian to the white race. And we'll be comparing African American to white as well. And it'll become more clear as well when we actually start coding this in R2, I think, as well. So if you're still not understanding it, hold on. We'll get you there. Don't worry. So what we're going to do right now is we're going to specify our dummy codes. And I'm not entirely sure if I've utilized the if-else function with you guys before, but just to kind of make things clear, what we're going to do is we're going to use an if-else function within a mutate function. So we do mutate, the name of the data set, then we're going to create a new variable called con2, in which we're going to say if-else, if condition is exactly equal to 2, we're going to code this new con2 variable as 1, else it's going to turn into a 0. And then with the con3 variable, if-else, if condition is exactly equal to 3, we're going to code it as this con3 variable as a 1, else it's going to turn into a 0. So let's go ahead and do that right now in R. So we're going to go ahead and do hashtag. Let's do part 1 dummy coding. Then we're going to do hashtag specify dummy codes for categorical predictors. Going to insert a new R chunk. So what we're going to do is we're going to overwrite the sleep data set. We're going to use the mutate function. We're going to indicate that it's a sleep data set. I'm going to press enter here. So we're going to create a new variable called con2 equals if else, if the con variable is exactly equal to 2, turn this con2 variable into 1, else it turns to 0. Then we're going to create another new variable called con3 equals if else con is exactly equal to 3, it's going to turn to 1, else it's going to turn to 0. So what's going to happen before we run it, I just want to show you, anytime that it's 1, this con2 variable is going to be a 0, and con3 is going to be a 0. Anytime that it's a 2, con2 is going to be equal to 1, and con3 is going to be equal to 0. And anytime that it's equal to 3, con2 is going to be 0, and con3 is going to be equal to 1. And I'll prove that to you right now. So we go ahead and run that. Oh, let's see here, what did I do wrong? Oh, I spelled mutate wrong. There we go. Right there. There we go. Okay, so now when we run this, it should occur. So now we have 4 variables. And we can see that con1 is 0, 0. Whenever it's con2, when condition equals 2, it's 1, 0. And whenever condition equals 3, it's 0, 1. And that's pretty much it. That's all we did. So the next thing we're going to do, we've already created our variables. Now we're just going to go ahead and we're going to run the model with these dummy coded variables. So it looks very similar to the way that we've ran regression models in the past, except this time we're going to be running it with dummy code. So we'll do hashtag run model with dummy coded variables. And I'm going to explain what these dummy coded variables are once we get to our model. So let's go ahead and do model 1, so M1. We're going to do the LM function. So it's going to be hygiene regressed on con2 plus con3, comma, data equals SLP. Then we create a new line and we're going to do OLS underscore regress M1. So let's go ahead and run that. So it takes a little while to load. So with our model, we're explaining 39.7% of the variance in sleep hygiene. And you'll notice that that's going to stay the same throughout all of our coding techniques here. So we have a significant model. Great. Now, remember, look at what our intercept is. It's 4.660. Remember that number from before? 4.600. That's the mean of condition 1. So in our model, it's the mean of condition 1, and we're saying that's significantly different from 0, essentially. Then condition 2 is really the difference between condition 2 and condition 1. And we're saying, is condition 2 significantly different from condition 1? And we say, yeah, condition 2 is significantly different from condition 1. Then condition 3 is 2.374. That's the difference between condition 3 and condition 1. So if you were to go and do the math and you wanted to actually calculate these, you can. You'll see that these will equal these coefficients down here if you just took the difference between condition 2 and condition 1 and condition 3 and condition 1. So what we're doing, and then additionally condition 3 is actually significant as well. So it's saying condition 3 is significantly different from condition 1. So you'll notice that we made a comparison between condition 2 and condition 1, and we made a comparison between condition 3 and condition 1. Where we didn't make a comparison was between condition 3 and condition 2. If we wanted to make that comparison, we would just rework our reference category so that it's comparing to either condition 3 or condition 2 here rather than condition 1. But really, we're just interested in saying how is the control group different from condition 2 and condition 3, essentially. And that's really all there is to dummy coding, is it? And you can add in other variables as well, and it works just as fine. You just interpret the model for when all things are equal to 0, then it's whatever your intercept is, and so forth. So this works with plugging it into other models with other variables as well. But we're going to keep it simple for today and just run it with the dummy coded variables. Then we're going to go ahead and now we're going to work on, I believe we should go, oh, this is where I explained to you what each of these means, so you have it for your reference and later, but I've already explained it to you. The intercept is predicted sleep hygiene when all x variables are 0, so participants in condition 1, and then condition 2 and condition 3. So let's go ahead and talk about what effect coding is now. So effect coding is very similar to dummy coding, except here you're comparing one level of a categorical variable to the mean of all the levels. So instead of asking, are two conditions different from each other, dummy coding is asking, is this condition different from the average? So while the rule in dummy coding is that all values are 0 or 1 are valid, the rule in effect coding is that all the values in any new variable must sum to 0, essentially. So I'm going to show you how this works now, but we're going to be using that if-else function to get that to work as well. This time, every time that condition is equal to 1, it's going to be turned into a -1 rather than a 0. And you're going to see how that's going to change up our model results. It's not going to change up everything about our model. I'll show you where the similarities are, but I'll also show you where the differences are from when we did the effect coding. So let's go ahead and do this. So we're going to do hashtag part 2. We're going to do effect coding. And then do hashtag specify effect coding for categorical variables. And I'll just do cond in parentheses. Okay, there we go. And we're going to insert a new R chunk. So what we're going to do is we're going to rewrite over the sleep data set. We're going to use the mutate function, and I can spell it right this time, SLP, comma, and then what we're going to do is I'm actually going to do this. We're going to do cond2.ec. So cond2, we're creating a new variable called cond2.ec for effect coded. If else, this is going to look exactly like the way that we dummy coded our variables originally. Equals 2, comma 1, comma 0. Then comma cond3.ec equals if else cond equals 3, comma 1, comma 0. Then, and I'll show you, we're going to go ahead and run this, and it's going to look exactly like our other variables. So currently right now it looks exactly like our cond2 and cond3 variables. There's no differences between them. However, we are going to change that so that every time condition is equal to 1, it's going to turn into a -1. So the way that we do that, simply put, do comma. I'm going to go down a couple lines here, and then I'm going to do cond2.ec equals if else if cond is exactly equal to 1, comma, and it's going to be a -1, else keep it as cond2.ec. Comma, we're going to do cond3.ec equals if else cond equals 1, comma, oops, that's a period, comma, turn it to a -1, else it's going to be cond3.ec. So I'll go ahead and just bring this back up. There we go. So now every time that a condition is equal to 1, cond2.ec is going to be -1, and cond3.ec is going to be -1. So we go ahead and run that and hope for no errors. Now we can see that every time a condition is equal to 1, it's -1. Whenever it's 2, it's 1, 0. It looks exactly like our dummy code. And whenever it's condition 3, it looks just like our dummy code as well. So the only difference now is when condition equals 1, it turns to -1. So now what we want to do is we're going to go ahead and run the model on our newly effect-coded variables. So let's do hashtag, let's do double hashtag, hashtag run model on newly effect-coded variables. So we'll do insert new arg chunk. So we'll name this M2. We'll do a assignment operator, LM, regress hygiene on cond2.ec plus cond3.ec, comma, data equals SLP, and then OLS underscore regress M2. So let's go ahead and run that. Here we go. So you'll notice that our R squared value didn't change at all, actually. So it's 0.397 here, 39.7% there, and it's still 0.397. So our R squared value hasn't changed at all from these effect-coded variables. We still get a significant model. And additionally, now things are a little bit different. So now it's saying, okay, so the intercept is 5.994. Huh, does that look familiar? Well, it should look familiar because that's exactly what our overall grand mean is. So our mean is equal to the grand mean now. Additionally, it's saying cond2.ec, it's saying, is condition 2 different from the grand mean? And it's different by 0.293. And then we say, okay, is that significantly different? Saying, yeah, condition 2 is significantly different from the grand mean. Then we have condition 3, and we're saying, how different is condition 3 from the grand mean, which is 1.041. So it's saying it's 1.041 points higher than the grand mean, and indicating that, yes, this is a significant effect. So essentially, condition 2 and condition 3 are both significantly different from the grand mean of in their hygiene scores, essentially. So I went ahead and I wrote out the interpretations here for you as well. So in effect coding, the intercept is the grand mean of sleep hygiene across all 3 treatment groups, and then I tell you what the difference is overall. So there we go. That's all there is really to effect coding. The third one is contrast coding. This is the one that I'm the least familiar with, so my interpretations might be a little bit shaky at first. I've personally never used this in my own work, but we're going to go ahead and just try it out anyways, all right? So we'll get through this, all right? So what is contrast coding? Contrast coding is used to compare specific groups within your variables. It's required that these contrasts are orthogonal. So remember when we talked about what orthogonal contrasts were before? Orthogonality means that the number of contrasts is equal to the degrees of freedom, so the groups minus 1. There's at least 3 groups that you can compare, and the pairwise products of the corresponding coefficients for each term sums to 0. So let's go ahead and run through that. So we have 3 groups. So we've matched that. There are at least 3 groups. The number of contrasts we have is equal to the degrees of freedom minus our degrees of freedom. So we have 2 contrasts and there's 3 groups. So yes, that's the degrees of freedom is 2. Additionally, we need our contrast to the cross product, the pairwise products to sum up to 0. So 0.5 times negative 0.5 is negative 0.25. Negative 0.5 plus times negative 0.5 is positive 0.25, and 0 times 1 is 0. So we did it. We reached orthogonality. So what we're going to do now is we're going to code our variables as so. So we're going to be first comparing condition 1 to condition 2, and then we're going to be comparing the mean of condition 1 and condition 2 to condition 3. And there's a lot of different other comparisons we can make. I think this one was just the simplest one to make with the contrast coding. Which is going to be comparing, the contrast 2 is going to be comparing condition 3 to the average of condition 1 and condition 2. So simply put, we go ahead and we run these if-else statements. For this one, it's going to be a little bit more complicated. We're going to be using nested if-else statements. So essentially what's going on is we're going to first be comparing contrast 1 versus 2. If else condition is exactly equal to 1, it's 0.5. Then we say, but if it's not equal to it, then if its condition is equal to 2, it's going to be negative 0.5, else it's going to be a 0. So it's a nested if-else function in there. And I'll kind of show you what's going on when we're actually running the code as well. So Let me go ahead and get to my notes here. And then we're going to go ahead and type this in. I'm going to type this in without any errors. So I'm going to do contrast. So let's do contrast coding. Hashtag, specify contrast codes. Okay, so I'm going to hope I don't have any errors in this. I'm going to be kind of concentrating pretty hard to make sure that I don't make any errors. So hopefully you'll be able to get this done as well. So let's do SLP. This, it's going to be mutate SLP, comma. Okay, so we're going to name a new variable called contrast underscore 1v2. So we're comparing groups 1 to groups 2 equals. We're going to use an if-else function. We're going to do cond is exactly equal to 1, comma, it's going to be a 0.5. Else, we use an if-else function again, and then we're saying if condition is equal to 2, is exactly equal to 2, and it's going to be negative 0.5, else it's going to turn to 0. Okay, so I think we got that first one down correctly. Then we're going to do contrast. This is going to be 3 underscore 3v12. So it's 3 versus groups 1 and 2 equals if else cond is exactly equal to 1, comma, it's going to turn into negative 0.5, comma, then we're going to use that nested if else. Cond is exactly equal to 2. Oh, so I almost made an error here. There we go. So because up there it's going to be cond equals 2, comma, negative 0.5, else 1. And so if I did that correctly, what we're saying here is that when condition is exactly equal to 1, it turns to a 0.5. Else, if it's equal to 2, then it turns to negative 0.5. Else, it turns to 0. And then for this next one, we're saying condition 3 versus 1, 2. We're saying if condition is exactly equal to 1, then we're going to turn it to a negative 0.5. Else, if condition is exactly equal to 2, it turns to a negative 0.5. Else, it turns into a 1. So I think I did that correctly. So we're going to hope that I did that correctly. Otherwise, we're going to have some troubleshooting we're going to do on this video. But it looks like it did correctly. So we have contrast 1 versus 2. So it's 0.5 times negative 0.5. So that would equal negative 0.25. For condition 2, it's negative 0.5 times negative 0.5, which is exactly what we're hoping for positive 0.25. And then when condition is equal to 3, it's 0 times 1. Yes, so we did it correctly. Okay, so that's going to take some kind of just copying on your part to get to that. If you mess around with these if-else functions, I think you'll have a better understanding of what's going on. But essentially, just know that we created it correctly, okay? So now what we're going to do is we're simply going to run this model with the contrast codes now. So do hashtag run model with contrast codes. So we're going to insert a new R chunk. So we're going to do M3, use an assignment operator. We're going to regress hygiene. We're going to do LM. We're going to regress hygiene onto contrast underscore 1v2 plus contrast underscore 3v12, comma, data equals SLP, comma, that's it. Then we're going to do OLS underscore regress M3. Here we go. And when we run that, there we go. We did it correctly. So notice again that our R squared didn't change. It's still 3.397. And what I'm actually going to do is I'm going to go ahead and go over here to the interpretation. So this is exactly what you should have up on your screen. Remember the R squared is 0.397. So notice that the intercept is the grand mean. So in contrast coding, the intercept is the grand mean of sleep hygiene across all 3 treatment condition groups. And that's a good way to know whether or not you did contrast coding correctly or not by seeing if it hit the grand mean. If it didn't hit the grand mean, it means that your contrasts aren't orthogonally contrast with each other. Okay, So our first coefficient, which is contrast 1v2, we're saying the difference between conditions 1 and condition 2 is statistically significant. So we're saying that there's a difference of negative 1.627 and it's statistically significant. For contrast 3v12, it's saying the difference between the average of conditions 1 and 2 is significantly different from condition 3, and it is statistically significant as well. And that's really all there is to contrast coding. Contrast coding, I'll be honest, I'm the most shaky on, but it's a really useful way. I've never had to use it in actual practice before. I use mostly dummy coding across all this, but that's essentially all there is to contrast coding. So I have some additional resources on categorical variable coding systems if you're really interested as well. Some things that I used to help me out when I was creating this lecture or learning categorical variable coding for the first time. Okay, so we're going to go ahead and start on to part 2. I'm going to go ahead and say you should probably start your part 1 of the assignment before moving on to the part 2. Okay, I'm going to go ahead and pause this video. All right, students, welcome to part 2, where we're going to be talking about nonlinear regression. So nonlinear regression is essentially the regression that's not linear, and it's exactly there in the name. It's regression where it doesn't follow a linear trend. So essentially, we can see a quadratic, or even a cubic, or even a quartic effect. Other types of nonlinear trends are long trends, form trends, and so forth. But essentially, as you can see in the middle here, this is a linear trend where it's just a straight line. Whereas over here on the graph on the right here, we can see that it's a quadratic trend in which we see that it's got one bend associated with it. Remember, it's the number of bends is the type of trend minus 1. And then we have the cubic trend, which is a cubed. And essentially, we see that it has 2 bends associated with it. So that's exactly what we're going to be looking at today. It's data that's not linearly associated with. And we're going to show some examples as to what that looks like. So let's go ahead and dig right into R, okay? So what we're going to do is we're actually going to go ahead and go into our Module 4 folder, and we're going to open up that project file associated with Module 4, okay? So we already have this. We're going to go ahead and create a new R notebook. Well, actually, first we're going to go ahead and download the data. So let's go ahead and go to Home. We're going to go to Module 4, Module 4 Lab. Do the cogtest.csv, download the cogtest.csv. Okay, we're going to do File, Save As, Browse, go to Desktop, go to Site 653, Module 4, and download there. We already have the sleep data in there already. There we go. And let's go ahead and create a new R notebook. I'm going to delete this unnecessary text. And we can go ahead and name this nonlinear regression. And we'll go ahead and output a table of contents, colon, TOC, colon, yes. And let's go ahead and name this. We're going to name this Module 4 Notebook. We'll name it nonlin reg. How about that? Nonlinear regression. There we go. Okay, and we'll see what we have next in our slide. So next thing we're going to do is I'm going to load up some notes here real quick. Okay, next thing we're going to do is we're going to go ahead and load up our libraries. Okay, so do hashtag load libraries. Insert a new R chunk. And we're not going to be using any new libraries. We're going to be using the OLSRR library, OLSRR library, psych, and library tidyverse. I think that should be good. So go ahead and run all that. Here we go, loading up the OLSR, psych package, and the tidyverse package. Okay, looks like everything loaded up correctly. I'm just going to press play to kind of get rid of that, that information. And then what we're going to do next, we're going to go ahead and do hashtag import data. So we're going to be using the cogtest.csv. So we're going to name this, we're going to insert a new R chunk. We're going to name this cog, use an assignment operator and do read underscore CSV. And in quotation marks, we're going to do cogtest.csv. We're going to do this. There we go. And look at our cog variable. So we have subject, practice, and score. So let's go ahead and I'll see. So in this data set, I think we've used it before, but we're going to be using it in a little different specification this time. But essentially, researchers were interested in the effect of time spent in practice on the performance of visual discrimination tests. Subjects were randomly assigned to different levels of practice, following which a test of visual discrimination is administered, and the number of correct responses recorded for each subject. 40 subjects were randomly assigned to practice of 0 minutes, 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes, 12 minutes, and 14 minutes. So now I want us to know, even though those seem categorical, we're going to pretend like they're actually a continuous variable for the case of this lesson, because there's enough of them that it acts like a continuous variable, essentially, is what we'll be doing. Okay, so we're going to be saying practice is a continuous variable, even though it's categorical in nature, but we're going to just be acting like it's continuous for the sake of this lesson. So let's go ahead and describe the data. Okay, and insert new R chunk. We're going to describe cog. Go ahead and do that. There we go. We got 40 observations. Mean practice score is 7. Our mean score is 16.38, and I believe it's the number of correct answers. I forget what the correct total number you can get, but it looks like it's around, maybe it's 30. It's 1 to 30, I would say, or something like that. So what we're going to do is we're going to go ahead and plot the data. And I'm going to get pretty intense with these graphs today. So let's do hashtag plot the data. And we're going to do hashtag as a linear relationship. So let me just go ahead and bring this up a little bit. Okay, so we're going to insert a new R chunk. So we're going to use ggplot, cog, comma, aesthetic, x equals practice, comma, y equals score. We're going to be creating a scatter plot with a geom smooth in there. So it's going to be geom smooth method equals quote lm, comma, se equals false. We're not going to have the standard errors show in our model as well. Then we do geom underscore point plus, we're going to do something called scale x continuous, and this is just some kind of preparing that I did in the last one. It's going to be limits equals c 0, comma 14. So we're setting the x limits to 0 and 14, comma, breaks equals seq 0, comma 14, comma, by equals 2. All that's doing, the sequence is saying, give me sequences from 0 to 14 and break it up by 2 points apiece. And you'll see what that looks like when we actually graph it. Then we're going to go and do labs. Title equals does more practice equal a better score, question mark, comma, subtitle equals overlay the best fit straight line. So this is a linear regression that we're fitting. And we do comma x equals minutes spent practicing, and comma y equals score. I kind of want to get a little bit more intense with the ggplots here so that you have some skills associated with it. So as you can see, we created a new ggplot. It just is going to run a straight line. Now we're saying to ourselves, does this best fit the data? We can see that, it does an okay job, but what we really want to say is, hey, would a quadratic line fit it better? So one with a curve associated with it, would that fit it better? And as you can see, 0, 2, 4, 6, 8, 10, 12, that's what that sequencing 0 to 14 by equals 2 did. It separated this out, so it's by 2, so that it gives me the scaling. So now what we're going to do is we're going to do the exact same thing, but we're going to set a quadratic line associated with it. So this is a curve with one bend associated with it. So let's do hashtag plot data with a quadratic function. Okay, so let's go ahead and insert a new R chunk. So we're going to be, again, utilizing a lot of features associated with ggplot here. So we're going to do ggplot, then indicate our data set, which is cog, comma, AES, x equals practice, y equals score, do plus, then let's do geom underscore smooth, method. So it's going to be method equals quote LM, but we're also going to set something called a formula. Formula equals, we're going to say y regressed on poly for polynomial x comma 2. It's going to say fit this y variable regressed on the polynomial of 2. So it's saying pretty much squared, comma SE equals false. We don't want the standard errors associated with it. So this poly x comma 2 is essentially what's setting this for a quadratic equation, comma plus. Then we're going to do geom point, so that we just have those points associated with it, plus we're going to do scale x continuous again, x continuous, and we're going to do limits equals c 0 comma 14 comma breaks equals sequence 0 comma 14 comma I equals 2 plus we're going to do labs title equals, let's go ahead and put this back here, title equals, in quotation marks, does more practice equal better score, question mark, we're going to do comma subtitle equals overlay a quadratic curve, comma, x equals minutes spent practicing, comma, y equals score. Okay, there we go. So this is a pretty intense ggplot that we set up, but it should have everything. And there we go. So what we've done is we've set a quadratic curve associated with it, and we're saying, and when we eyeball it, we're saying, yeah, that kind of seems like it fits a little bit better than a linear curve that we showed earlier. Like, yeah, a linear curve kind of captures it, but a quadratic curve is like really showing that, oh yeah, we're really hidden in between every single point there now. So what we're going to do is we're going to set ourselves up so that we can actually run a linear regression model with the quadratic curve associated with it. And we're also going to set ourselves up for a cubic curve to see if that happens well. I didn't do the cubic curve here. I don't think we need to do it. I think that the quadratic curve is the best, but we're going to just run a cubic curve as well just to see if it works okay. So how are we going to do that? So we currently have 3 variables in our data set. What we're going to do is we're going to mutate our practice variable so that there's a quadratic form of it and so that there's a cubic version of it. So the way that we do that is we're simply going to do hashtag mutate practice variable for polynomial regression. And I'm going to put a colon here, get quadratic and cubic variables. Before we do that, I just want to make sure I'm caught up on my PowerPoint here. So we described, we did that, we plotted the quadratic relationship. So I have it all here if you want to copy it down. And then now we're going to simply be mutating the practice variable into a quadratic and cubic now. So we're going to do insert, a new R chunk, we'll do cog, and we're going to create an overwrite the cog object, mutate cog, comma, we're going to do practice 2, so that stands for practice squared equals practice to the second power, comma, practice 3 equals practice to the third power. What we're going to do is simply get a squaring and a cubing of our practice variable when we do this. So let's go ahead and run this. We're going to go from 3 to 5 variables. There we go. We have 5 variables. And as you can see, when it's 0, it remains 0. When it's 2, practice 2 goes to 4. Practice 3 goes to 8. when it's 4, practice 3 goes, when it's 4, practice is 4, practice 2 goes to 16 and 64, and so on and so on, and then it becomes way more exuberant as we get to 14, okay? So, go ahead and save that. And then, what we're going to do is actually going to look pretty similar to when we did polynomial contests, is we're simply going to be running the models and comparing them all with each other. So, what we do is we simply do, we're going to run it first as a linear model. So hashtag run, let's do run linear, quadratic, and cubic models. We're going to insert a new R chunk, and then we're actually above this, we're going to write hashtag linear models, linear model, and we're just going to run to see what this looks like. So we're going to name it mod lin. Create a new object called modlim, LM. We're going to do score regressed on practice. So just practice, comma, data equals cog. And we're going to do OLS underscore regress, mod underscore lin. So we're going to go ahead and run this and see what happens. Okay, so our model is explaining 85.6% of the variance in score. So just practice alone explains 85.6% of the variance in score. And then we have a significant model. And then we don't really care too much about the intercept, but what we're saying here is that, okay, yeah, practice is significantly associated with score. Okay, that's great. So what we're saying is we essentially mapped on this model, but what we want to do is now map this model. So the way that we do that is essentially we take our practice variable that's squared and add it to the model. So really what we can do is we can copy and paste all this and make a few changes to it. So then let's do hashtag quadratic model, and then we can go ahead and paste this, and then we're going to do mod, we're going to name it quad, and then we'll name it quad down here too, so that when we regress it, and the only difference between these two models is we're going to do plus practice 2. So now when we run this, we get a new model, and now we're explaining 97.4% of the variance in our score variable. So what we're testing now, we're just saying, is this a significant model when we run in a quadratic term? And what we're saying is, okay, yeah, our linear models still remain significant, and this is significant as well. It's saying, yeah, there's a quadratic function that's associated with this. So this curve has one bend in it associated with it. Now, all we need to do is run the cubic model, and essentially the same thing as we did here. So I'm going to go ahead and copy this, and then I'm going to write hashtag cubic model. You insert a new R chunk, or actually don't need to insert a new R chunk because I already created that chunk. And then we're going to name this mod CUB. Change this to mod CUB. And then all we need to do is add in plus practice 3. And then we run that. And we're going to see, is it significantly different from that? So we're explaining 97.5% of the variance in our outcome variable. It's a significant model. However, when we look at this, now when we add in practice 3, it makes our model insignificant, or it's insignificant, and it even made the quadratic trend insignificant as well. So what we're saying here is, yeah, actually, adding in the cubic model the cubic term doesn't really add anything to the model. However, this quadratic term seems to add a significant amount in there. And what we can do, if we want to, I don't think I even have this in the slides actually. So I went ahead and I explained everything in here. So starting with the linear model, then the quadratic model, then the cubic model, and that's the end of the slideshow. What we also can do is use an ANOVA, use ANOVA to compare the models statistically. So you can go ahead and do insert R, we do ANOVA, and then we do mod underscore lin, comma, mod underscore quad, comma, mod underscore cube, and we should be able to compare. So as we can see, the second model, which is our cubic model, is significantly different from our first model, saying, yeah, that's more confirmation. Yes, the quadratic model is the best model to fit this data, whereas the cubic model is not explaining significantly more. So again, giving us more confirmation that yes, the quadratic model is the best model to fit our data. So if there's a bend to the curve in our data and it fits better than this linear model. And that's really all there is to fitting nonlinear models. I know that was a little bit shorter than the other lesson, but it's actually quite not too bad of anything to do, really. And you've seen a lot of this already with polynomial contrast. So I'll go ahead and say that there's an assignment for you up on Canvas in the Module 4. Module 4 assignment.pdf, and you can go ahead and start working on that and let me know if you have any questions. Thank you so much.